Good evening, sports fans. We have an interesting little number theory question, not particularly difficult, but one that you got to do a little bit of work. Now, what we have here is a question. We have three integers that depend on n, and n is considered to be a positive. It could be 0 or positive, I suppose. I don't think it makes much difference here. But such that all of these three numbers, notice 7n minus 2 is an integer, 8n minus 5 is an integer, 9n minus 1. We want to know if there are any n such that all of these guys can be prime, okay, meaning they have no divisors other than 1 in the number itself, okay, and we're talking about positive, the standard definition of positive prime numbers here. Now for n equals 1, that actually induces the list of numbers 5, which is prime, comma 3, which is prime, and then 8. So right here, here's our rascal 8, which is composite, right? So n equals 1 doesn't work. Let's maybe try n equals 2. So for n equals 2, we get the list of integers. 14 minus 2 is 12. 8 times 2 is 16 minus 5 is 11. Okay. Then 9 times 2 is 18 minus 1 is 17, right? So you see in both cases, 2 of the 3 values, if I did make my calculations correctly here, are prime values. 5 and 3 were prime in this list, and 11 and 17 are prime in this list. So can we hope for the possibility of there being an n such that all 3 are prime? Now let's get busy proving this. It turns out to be fairly straightforward. One thing that's super useful right here is that when you sum all these up, you see you get 24, 7, 8, and 9. 15 is 24, and then 8. So this is an even integer, right? Now you might not think, what does the sum have to do with it, right? But then we have this very useful result. If 3 integers sum to an even number, at least one of them is even. And the real reason for that is just that, let's just say you have 2a plus 1, 2b plus 1. These aren't consecutive now necessarily. Okay, so 2b plus 1, and then 2c plus 1. Okay, so these are 3 arbitrary odd integers. Notice that they couldn't sum. If you add these up, you would get an odd number, right? So these all sum up to odd sum. Let me write it like that. Okay. So for that reason, at least one of the integers has to be even, okay? And that's what we got here. We have 3 integers. Now notice that this guy right here is always odd, right? I'll just write that down. That's pretty clear, right? An even minus an odd is an odd. Okay, so what we would do right here, and I guess I can just write right up here, one of them has to be even, but we're looking for primes, right? So we would have to have 7n minus 2. Now remember, this is kind of fun here because there's only one even prime, and that's 2. And the only possibilities would be 7n minus 2 equals to 2, or 9n minus 1 equals to 2, right? So you see, in a way, you got tons of leverage right here because they have to be prime. So this one's always odd, all right? But notice that there's no solution to this, right? There's no solution to this or this. You would get n is equal to a fraction here. You would get n is equal to what? 4 over 7. N is equal to 1/3 right here. So you see, neither one of these, which would be the only possibilities, can be equal to the only even prime, and that follows from this lemma right here. So the answer to our question, it's got to be no. Okay, again, a little bit of logic there, because otherwise, what would you really do here on this problem? You know what I'm saying? What would you do? We saw these first 2 examples at the beginning where 2 of the elements in each list were prime numbers, right? So that opens the door to the possibility of there being 3 of them all prime somewhere. We've only checked the first 2 integers, right? Way out there like 1,000, maybe it works, This right here was, you could have, if this one could have been even 2, then we would have just set all 3 of these equal to 2 and found there would be no solution. So this wasn't that big a help, other than we only had to check 7n-2 and 9n-1 for equaling 2, right? And again, there's no solutions to either of those. And so the answer to the question is no. Anyway, I thought a fun little problem. It's maybe junior level competition, say for SMO. I don't. Maybe it's an easy problem, but if you don't stop and think about it, you might not notice that this lemma is useful. When I first looked at this, I spent quite a bit of time on it, not knowing to sum them all up, and then get this lemma that really is quite powerful for this particular problem. It doesn't seem like it would be related at first glance, but it turns out to be extremely useful. But anyway, the result is no. Thank you for viewing.